Okay, now we will study the titration today. Okay, so hope you guys are fine, right? And I hope you have watched the video that whatever I have given you yesterday. But now let's go deep dive into the titration. Okay, so before studying the titration, let's see that let us discuss a problem, right? Suppose you work as a process chemist in some pharmaceutical industry, and you have these drums, right? You see that this is the chemical inventory, and these all these blue drums present the some weak monoprotic acid. Okay, there's weak monoprotic acids. Okay, these all are the weak monoprotic acids. Look at that. But unfortunately, look at that. Some of the drum, the labels are missed. Okay, we don't have label here. We don't have label here. Means that what is the field on those drums? We don't know. Okay, what filled in that drums we don't know. Okay, guys, so so it means that you have to find what is filled over there, means that what is what contained inside that containers with missing labels. So in these unlabeled packs is unknown, but the list of acid is known. But however, we know that what is the list of the acid, means that whatever the acid present here, we have that list. A few of them, look at that, it has no label. This has label, but this guy has no label, right? This many of them are missing, and they all are weak monoprotic acid, that we know for sure. Now let's see the list here. These are the acid, list of acid, and whatever you have missing are any one of them, any one of them. Okay, but we know that the molar mass of these, right, we see that 60, 122, these are molar mass, and we also know the pK of these acids, and these any one of these is in filled in that blue drums. So my question is, how do you find out? So you are a chemist, that's why we have many ideas. Okay, many analytical techniques to find the unknown whatever is here, but one of that analytical technique is titration. Okay, easiest and very traditional is titration. Okay, we will do titration, and then we will find the what is unknown here, how much concentration is there. We will do the titration. Now let's go to the titration. Generally, what is titration? Well, the titration is an analytical method in which we find the concentration of the unknown sample by reacting that unknown sample with a known standardized the value. Okay, known standardized reactant. Okay, suppose that if you have is unknown is Ha. Okay, if this is your unknown, okay, let's go to here. If this is your unknown, suppose this Ha is your unknown, this is unknown, we will react that with a known in NaOH. This is a weak monoprotic acid. We will react with that NaOH, and NaOH is, for example, it is a known, its concentration is known, 0.1 m. Okay, we know that this is NaOH, its concentration is this. We will do the reaction between Ha and the NaOH, and we will find the how much mole of NaOH, how much NaOH necessary to neutralize the sample of this guy. Okay, let's say 0.344 gram we take from this unknown one, and we react with that NaOH, and the reaction give me, for example, 21 ml of NaOH. Okay, we find that the NaOH, how much NaOH is consumed, and that we will convert it into the mole, and that is the mole equals to that much gram. Do you know? Because the reaction is Ha plus NaOH, right? Okay, this gives you NaH plus H2O, right? So this is your salt, and this is your unknown, this is your known. So but what is the molar ratio? Look at that, 1 mole of Ha is equivalent to 1 mole of NaOH, right? Using that relation, roughly using that relation, that estimate, we will find the how many moles of this unknown are reacted. Okay, then when we know the mole, we know the mole here, we have the gram here, then molecular mass with the gram per mole, and if we find the molecular mass, we will compare that to our unknown solution from the list whatever we have given, right? Okay, that is your titration. Okay, so that's the method of titration. It is finding the concentration of the unknown by the help of the concentration of known one after reaction between them. Okay, so whatever is your standard solution, whatever the delivered using a burette or known solution, that is the titrant, and what is you have in the flask means that that is the analyte or titrate, we will say that, because we will use the burette and the flask here. And what is the standard solution, known solution, that generally we will deliver by the using burette, and that is titrant. And that's why we are finding the volume here, not any other things, volume. So this method is not the spectroscopic method or any other method. This method is the volumetric method. Okay, this method is the volumetric method. So that is the titration. Okay, now let's go to the what is the experimental setup of the titration looks like. Okay, let's see, the experimental setup is this. See that here it has the unknown acid. We will measure in the gram and we will make the solution. This has the unknown acid. Okay, we will fill that known concentration here, that is the NaOH. We know that how much, what is the molarity of NaOH, and we will put few drop of the phenolphthalein here, that is the indicator. And that indicator will show us, will tell us that hey, the reaction is complete, right? By showing, by changing the color, we use some few drop of the one indicator, and that indicator will show us whether the reaction is complete or not, and it will change the color if reaction is completed. This is a general titration setup. Okay, now let's go to one example and then you will understand better what we will do in the titration. Okay, so let us suppose that this is your experimental setup. You see that in the burette you have filled the NaOH, that NaOH is 0.1 m, and you do the titration, you have the phenolphthalein also here, means the indicator is also here. This is unknown acid. You run down that, you open that valve, and you mix that NaOH with that acid, and there is a reaction. Okay, and finally at the end of the reaction, when there is a complete neutralization, 100% neutralization, then it will change the color from this blue to pink. See that color is changed, and the neutralization is finished, means all of the mole of this acid is consumed by this NaOH. Okay, nothing of the trace of the acid is left behind here. A single molecule is not also there. All the molecule of acid are neutralized by NaOH, and when that happens, when that color change happens, you have total consumed is 21 ml. This is one example. In a titration, 21 ml of 0.1 m NaOH was consumed to completely neutralize the 0.344 gram of unknown monoprotic weak acid. What is the molar mass of that unknown sample? Match the unknown acid in the given table, whatever the table last time we have seen that. Okay, now let us do that. Let's do that. Okay, so oh, so sorry guys. Okay, now let's do that. Okay, so whatever is NaOH, 0.1 m NaOH, that is, and how much ml? 21 ml consumed, right? Means that, look at that, can you convert that into the mole? Easily. Okay, now what is the gram of unknown sample? That is 0.344 gram, right? 0.344 gram. That much unknown is used. We know the gram mass, you can easily take the electronic balance, right? Now let us see the reaction, what the reaction is. The if you see the reaction, right, and see the reaction. Now let me change the color here. Okay, so now let me change the color. Okay, now reaction is Ha equals, why I write Ha, it is a monoprotic acid, that's why I write Ha plus NaOH AQ gives you NaA aqueous plus H2O liquid, right? Look at that. Now, what is the molar equivalence of this Ha and NaOH? 1. 1 mole of NaOH is equivalent to 1 mole of Ha, 1 to 1. If 10 mole of NaOH are consumed, then your unknown is also 10 mole. Okay. So now, but let's see that how much mole of NaOH is consumed. Okay, 0.1 m means 0.1 mole per liter, right? So how much mole is consumed? 21 ml equals to 21 ml times, let's multiply with the molarity, 0.1 mole per liter, right? But you have to cancel ml and then convert that liter into the ml. Okay, this is equals to 21 ml times 0.1 mole, okay, divided by 1000 ml. Done. So what, and let me go here, then how much mole is this? Is, I calculate that 2.1 times 10 to the power minus 3 mole. Look at that, NaOH is that much mole. But if NaOH is that much mole at the end of the neutralization, then we have the monoprotic acid is also the same mole, right? That's why mole of Ha equals to same thing like that. Okay, 2.1 times 10 to the minus 3 mole. Done. If that is the mole, then what is the molarity? What is the molar mass? Molecular mass, look at that, gram divided by mole, is that is the molecular mass. Okay, gram divided by mole. Now let's say that molar mass of unknown is equals to gram by mole is equals to, what is the gram? What is the gram? Gram is 0.344. 0.344 gram by what is the mole? That is 2.1 times 10 to the minus 3 mole. And that is equals to 163.8 gram per mole. Now, let us compare that value to the list. Okay. Okay, let's see that. Now, list here. So, list, look at that. 163.5, 164.1, right? Trichloroacetic acid, 163.5. 3-chloroheptanoic acid, 164.1. Okay, now let us do some analysis here. Okay, let me first of all clear 160.8, right? Okay, now I have remembered that. Now let me clear all that. Okay, so look at that. What is the molar mass? Molar mass of unknown we find from the titration is equals to 163.8. But in the list, if you see in the list, okay, trichloroacetic acid, trichloroacetic acid, its molar mass is 163.5, and 3-chloroheptanoic acid, its molar mass is about 164.1. But your molar mass is that, right? What is the dilemma here? Two are same, all others are scrutinized, guys. Look at that, all others are scrutinized. You see that 163 in that range, these two only, all others are gone. We are sure that, we are 100% sure that all are not. But this can be either that, this can be either that. Okay, so in that situation we have to do other things also. Now let's see in the list again here. Look at that, we can easily get the molar mass of unknown, right? You have learned that. Now we also can get pKa from the titration. Now let us find the pKa. If we find the pKa, suppose from the from titration, pKa is equals to, suppose from titration your pKa is 4.1. Look at that. What is the pKa 4.1? This 3-chloroheptanoic acid has pKa is 4.08, means 4.01 is very close to 4.08, right? That's why what we will say that this 3-chloroheptanoic acid has pKa 4.1, 4.08. That is the experimental value, published value, whatever we can find from your appendix. And trichloroacetic acid has pKa is 0.71. Look at that, pKa is 4.1, pKa is 4.08, means that 4.1 is same. Mass is 163.8, 163.1, both are close. That's why what is that unknown? Unknown is equals to 3-chloroheptanoic acid. That is your unknown in your blue drum. Okay, so this is the this is actually application of the application of your titration. Okay, now let's go further. Let's go further. Okay, that we know that everything we found out that, but these are everything we done. Now let's go further. Okay, Let's go to two things: end point of the titration and the equivalence point of the titration. To understand that, first of all, let us ask, okay, let us ask that how do you aid that? Because before that you don't have color, but at the end point you have a color. That's why we know the total concentration consumed. But how actually that work? Okay, now let's see here. We use indicator, right? Okay, we will use indicators, but there are many types of indicators. Okay, now let's see the indicator. Okay, let me show you the list of indicators. This is one indicator, thymol blue first, that can show you color red acid, and it will show you yellow color on base. Similarly, all others also, right? Bromo methyl red, that will say yellow color in acid, blue color in base. Similarly, phenolphthalein, that is widely used. Phenolphthalein is, that will show colorless, no any color in acid, but pink color in base. This is very nice, right? And what is its pH range? 8.2 to 10. Okay, that is its pH range. Means within this range, it can change the color. Okay, and stay that color after that. Means it will have a dark pink color, type of dark blues pink mixed after 10. Okay, so we are using the phenolphthalein. Okay, we are using the phenolphthalein, and now let me draw here what is happening exactly. So you have, this is a butyrate, this is your butyrate. Okay, this is your butyrate. You are dropping down the sodium hydroxide. This is sodium hydroxide, and you have this flask, and this is filled with NaOH. Okay, this has the acid Ha. We don't know, unknown acid. Okay, and let us suppose that this is your end point. This is your complete neutralization point. Okay, here everything is filled here. Everything is filled here. Okay, this is acid is filled here. You see that acid filled here, acid have been filled there, right? So now when you completely neutralize these all of the molecule, then this point to you is your, for example, 100% neutralization, means a theoretical neutralization. Okay, suppose that you drop 5 ml and you neutralize that 5 ml. Suppose this is the neutralization portion, means how much is reacted and neutralized, that is your salt. That is your salt. Okay, so that much acid is still remaining. Can that phenolphthalein, whatever you have put their indicator php, show color? Can show color? No, it doesn't show any color because still acid is there. Let add more, let add more, and you neutralize that much portion. Can it show color? No, it don't show color again. Let's suppose that it neutralizes all of that, 100% of that, nothing left behind, everything get neutralized, and you have 100% here. Salt is here, 100% salt. Each and every molecule of your acid has been neutralized. Can it show color? I don't know, but let's see that what color. Now php only show color if pH of this thing is greater than 7.999. Okay, this is weak acid, and at 100% neutralization, suppose its pH is 7.99, it still will not show any color. But what happens, the magic after that? Okay, and this was theoretical, was suppose it should be suppose 21 ml. Okay, theoretical value by mathematically calculated value, that is true value, exact 100% correct value is 21 ml, suppose. But we cannot monitor that because we cannot change the color at that point, we cannot visualize by eye. How do I know that? But once you have some clue, we are very close to that point, then we will slowly add. We will not add much, but we will add drop by drop. And suppose we add a half drop. Let me zoom that here, half drop. This is half drop. Half drop means about 0.0125 ml. Okay, half drop means at least that much ml, very small amount. If we add that, what will be the basicity or acidity of that solution? Now previously it was neutralized, neither acid nor base, but now you are adding the base further, means now your solution is basic. and your solution will have pH more than 7.99, because previously 7.99. Now you have added the base and it will be more basic, and it will cross the threshold limit of that phenolphthalein, and it will show you the color. Now here it will show color. Now let's draw that again better again. Okay, let me clean that. It looks ugly. So now let me uh, do that again. Okay, so here is here is you have a theoretical value. It should be 100% correct. That is 21 ml. It should be that, but that is no way to get that. We don't have any technique to get exactly amount. It is an experiment, right? In experiment we have very close amount, but not the book amount, right? Not the 100% mathematical amount, or that theoretical. We cannot do that. We don't have any idea to get that in the laboratory. In laboratory we have to do some experimental value. So after adding half of the drop, your concentration will be, look at that, your concentration will be 21.015 ml. Look at that, very close they are, right? 21 and 21.015 ml are pretty much close, right? You don't have much problem, accuracy problem. Okay, so here you show the color, but here you don't see the color. You don't see the color here, you see the color here. Okay, so it means that you cannot know, you can realize that, okay, my reaction get end before 21.015, just before 21.015, just before that. It means that it could be 21 ml. We can realize that, but if you use this value, still it is not harming our accuracy. Okay, 21 ml, if last time if you calculate that, 21 ml gives you what, 163.8 gram per mole, your molar mass, right? And 21.015 ml will give you also very close, right? 163.4, for example, 6 gram per mole, right? That much will be difference. Okay, this difference is decimal half of, after decimal means it is not even less than 1, right? Sorry, it is not even 1. 1 is the mass of the hydrogen atom. What is the difference is even less than the hydrogen atom. But there is no any atom exists in the planet whose mass is less than hydrogen atom, right? Smallest mass atom is the hydrogen atom, means you don't have half hydrogen. It means that you can write both is same, 163.8 and similarly 163.6. That's why these 2 points you will assume very close, very close, and you will use this also if this is theoretical. But instead of this using theoretical one, use the experimental. It show the color, it don't show the color. This is the theoretical, theoretical theoretical equivalence, right? 100% neutralization, and that point is said to be the equivalence point. Okay, and at this point where you see the color, that is said to be the end point, because once we see the color, we have to stop the reaction and we find that how much ml is consumed. Done. So we will again go to the technicality of this thing. Okay, and again still there is some technicality left behind. Okay, one question again is, here you know that, right? I am very very close to, okay, I am very very close to this, in this equivalence point. You know that, that's why you start very slowly, you add even a single drop or half of the drop, right? If you don't know that I am reaching to the close, then how do you add the half of the drop? You will add 3 4 5 ml and you messed up, right? How do you get that here? How do you know that you are very close to the end? Now I have to be very careful. How do you know that? Okay, look at that. This is, if you think about that, you run down, run down, run down, and about 21 ml, if it is close to 21 ml, you have to slowly add very, even a quarter drop, even half drop, this hanging drop, just wash that. That also works. Okay, and what will be the end point color? Look at that. End point color looks like this much light. Means how much small base you have added. Can you imagine? Very very small. Look at that, one hanging drop is here. Even you are not completely putting that hanging drop also, half of that hanging drop also you are putting that. Okay, so now that is okay. Now let's go again, how do you know you are very close to that? Now let's plot that again. Let's draw me that again. Okay, how you know that you are very, very close to that. So, okay, let's suppose that, let me take another color for this end one. Let's say this is the end point. Okay, guys, that's the end point. That's your true equivalence point. It is a theoretical, exact, whatever you say that, exact value. And somewhere after that, very close to that, you will have an end point. Okay, let's suppose that you will have end point very close to that. Let's say this is your end point. Okay, this will be your end point. Okay, but if you know this, if you know that I am very close to this, then no way to get this one because color not change. You will slowly add very, very small addition will give you color. That's fine. But how do you know that you are very close to that? Yes, we know that. Let's see that. How do you know that? Okay, let's see how do you know that. Now you are adding the sodium hydroxide. Okay, this is your pipette tip. Okay, this is your pipette tip, and you are adding sodium hydroxide, and you are at here nothing at the beginning. Let's suppose that this is this much neutralization you are doing that here. But what happen is, if you add that sodium hydroxide at the beginning, let me take that this one, these are the molecules of the acid inside the solution. Okay, these are the molecule of acid inside the solution. At the beginning, when you put the drop of these, then that will strike on the inside here, and if you get strike inside there, that sodium hydroxide, then it is very easy for that sodium hydroxide to get nearby acid. Look at that, one acid is here nearby because there are a lot. So it it will appear the color because it will displace few of the atom here, and the locally when it strike that for very, very small moment of time, that local region, right, local region, it is neutralizing two or three, but left are others are left behind. Local region here, you will show the color. Okay, guy, but that color will disappear very fast if you just shake, disappear. Suppose that you neutralize that much and that color disappear in 0.5 second, very fast. You can realize that. Okay, when you do the experiment, you will realize that, guys. Okay, of course you will see that how that color is disappearing fast and slow. And if you add that much, means that this much already have been neutralized, and it color disappear in 0.5 second. Now you find that this is disappearing in 1 second. It stay for a while and then disappear because you already have neutralizes these, you have less amount of these acid or hydronium ions are present there, right? So you already have neutralizes these many hydronium ions, and very small number are left behind. That's why it takes a little bit time for diffusion, because very few are nearby that. So probability of hitting that, getting close by whatever your this the hydronium ion is little bit slower, right? That's why it takes one. And now let us go further again. And if you have this, then you have very small chance, one, two, three, very small number of hydronium ion left behind. That's why this could be 2 seconds. Okay, if you become very, very close to that, let's see that very, 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 very close to that, it may take even 4 seconds. It disappears slowly. It may take it 10 seconds. You shake that and leave it, and it disappear in 5 seconds, for example. Then you will know that if it disappear very, 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 very slowly, then you know that I am very close to here. Okay, then when this cross, color never go, color will be always there, it never go away, right? Slowly. Now how, what is happening here, color disappear like that, and it color go here, but here it never go away, right? Then that is your, when the color is very, 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 very light color you will find, but that will never go away. But here color go away after even 20 seconds. I have seen that 1 minute also it take to go away the color, sometimes 2 minutes also, right? But if you put hanging half of the drop, quarter of the drop, that color will be very light pink. Look at that, and it never go away. Okay, and that's we know that then that is your end point. Okay, so if you find the end point, If you find the equivalence point, then you can easily you can easily find the molecular mass. Now after that, so at this point, whatever we learned here is equivalence point. Equivalence point, we learned that, and end point, we also learned that. Okay, how to calculate the unknown concentration, we also learned that. You know that you find the how much mole of NaOH are consumed, that much mole is your unknown if it is monoprotic acid. I will discuss here what will happen if diprotic acid, triprotic acid. Easily you can find. Okay, now unknown concentration, now molar mass. Okay, these many things it is clear right now. But molar mass is not alone sufficient to predict whatever the chemical formula that is, right? We have seen that. Molar mass is 163.8 gram per mole, but that is not sufficient. That's what you will do is you will find the pKa also. Okay, you will find the pKa also. Then how do you find the pKa? You will do the pH titration. pH titration. Previously you have PHP, phenolphthalein, as an indicator, and it was changing the color. But right now you are using the pH meter. You will see that the equivalence point. How you will find that the equivalence point. Previously equivalence point find by color change. Now equivalence find by the pH change. Okay, it's the same thing. So when you find the pH, when you find the equivalence point, then you will use the Henderson-Hasselbalch equation. And now let's go how do we do that pH, and then we will go to the diprotic, triprotic if we have time today. Okay, now how we will do the pH titration. Now let's see that. First of all, pH titration, you remember that we need two things. One is the equivalence point. One is the equivalence point, and other is we will use the Henderson equation. We need the Henderson-Hasselbalch equation. Okay, second we need the Henderson-Hasselbalch equation. So we need these two things. Okay, so first of all, let's say how do we know the equivalence point and how we do the pH titration. We are not using any indicator, but now let's go how do we do the pH titration. Let's see this figure. Okay, this is the setup of your pH titration. You have this butyrate is here, right? You have the butyrate, and you have this analyte is here, right? Unknown sample is here, and you have this pH electrode is here, and you are measuring the pH. Okay, so now you will run down this NaOH, right? This much NaOH is already consumed. You see that this much NaOH have been consumed. Okay, so now you add the NaOH and measure the pH. Add the NaOH and measure the pH. Okay, first of all, you have not added any NaOH. Its pH is 2.5, and add 5 ml. Its pH is 3.8. Its 10 ml. Its pH is 4. 15 ml 4.1. 20 ml 4.3. 4.4, 4.7. Now let us see here 9. 4.7 to 9. It's a big jump, right? That big jump point is the equivalence point, guys. Look at that. This is the big jump, right? It is a 9. See that? Here is a 9. That big jump is the equivalence point. That big jump is the equivalence point. Do you know? Look at that. That's why 25 ml is your equivalence point. This 25 ml is your equivalence point. Makes sense now? Okay. Because why that is equivalence point, I will show you in a minute. Okay. We will again go to what is happening on that beaker. Okay. So other thing we learn here is, look at that. That beaker has some buffering property in between also. Okay. In that beaker means what is the reaction here? Because this is the buffering. Why? Because we are using weak acid and a strong base. That's why sometime for 10 ml to 24 ml it behaves like the buffer solution. That's why this region, look at that, how much pH is changed, very small pH change. However, you are adding NaOH, more mole of NaOH, but pH doesn't change. It means that this is your buffer region, right? And you can see that here also 4, 4.1, 4.3, 4.4. This is the buffering region, and you can show that here. This is your equivalence point. Now we learn What is equivalence point? Okay, so let us tell you why that big jump equivalence point has. Okay, and why that buffering value also. First of all, now question is why buffer, why it is being buffer, why that is behaving as like the buffer in that region, and why big jump is equivalence point. Let's understand that. For that, let me draw again. Okay, guys, again is here. Okay, first of all, buffer, what kind of solutions are buffer, what kinds of the mixtures are buffer? Weak acid, this is the acidic buffer. Okay, we said weak acid plus salt of this weak acid and a strong base. Salt is obtained from that weak acid and reaction between weak acid and strong base. That salt which you get by reaction of this weak acid and strong base, and that weak acid itself, if you add these two and make the mixture, then that is the buffer solution. Okay, that we learned from we learned that. Okay, now let me erase that. Okay, and I will give you one example. So now let's see that. Okay, weak acid. Okay, you have the weak acid, you have the weak acid. Say, let's suppose the CS3COOH plus NaOH. That will give you CS3COONA plus H2O. But if you do that reaction, you are titrating here. You are you are titrating, means you are running down the you are delivering the NaOH here. Now let's say this is your equivalence point. Suppose equivalence point. This is now what is happening below equivalence point. Okay, what is happening below complete neutralization? Now let's see that. Suppose that you neutralizes that much. It means that here is you have salt. What is that salt? This guy. Okay, and what is this much? This guy. What is this guy? That guy is acid. You see that? What is the buffer solution? Buffer solution means acid, weak acid, means this is weak acid. That's why acid plus salt. If that both thing are in your beaker, then that is the buffer solution. Okay, so look at that. In that also, during your titration, you have both thing are there, salt plus acid. It will be a buffer, but it not be the perfect buffer. That's why it is kind of buffer. Look at the 2 and 4, it is still stabilizing, but it is a not good buffer, right? Its capacity is not that much. Once you go up, look at that. Let us suppose that you have neutralized that much. If you have neutralized that much, suppose this is 10 ml and you neutralize that much, again you have this much salt and you have this much is acid, right? So what is happening here is you are getting the mixture of salt and the acid in your titrant. That's why it behaves like the buffer, right? So at near the end, it will not behave like the buffer, right? It will jump. Why this jump? Up to this point, your pH could be, for example, 7. Okay, but you have added enough NaOH. That's why it will cross that here, and it will show you big jump. This is the 9 then. Whatever below that or nearby that, what is the nearby that? Because you are adding 5 ml. If you go to 111 ml, you are getting the jump from 7 to 9. Okay, but you are getting 5 ml. That's why at 5 ml it is very close to this point. That's why you are getting the 4.5. And if you add 5 more ml, everything get neutralized, and you are getting 9 pH. But you don't have to worry about that, right? This 9 pH is your equivalence point. So now we have the answer why big jump is there, because everything get neutralized and you have basicity is high. That's why it give you the high pH. Okay, now both answer now. But after that, let's use the Henderson-Hasselbalch equation. Why we use that? Okay, so we find out the equivalence point. Okay guys, equivalence point, that we will use that information of the equivalence point. Okay, but before that, Let's see that Henderson-Hasselbalch equation. What is the Henderson-Hasselbalch equation? I think you guys remember Henderson-Hasselbalch equation. We have used this in buffer solutions. We have monoprotic, diprotic, weak acids. These lots of place we use that Henderson-Hasselbalch equation. Okay, what is that? pH is equals to pKa plus log of conjugate base by acid, means log of salt by acid, right guys? Okay, if you remember that, we have discussed about what happens if conjugate base and conjugate acids are equal. We have studied that. Okay, suppose that at some point, because we are neutralizing that, half neutralized, quarter neutralized, we are looking that, right? Suppose that at some point you have a concentration of salt is equals to concentration of acid. Suppose you have that. What is happening? Salt and acid concentration is same, means that these two cancels, and this is 1, this is 5, this is 5, that means this is equals to 1, right? You have that term is log of 1, right? But log of 1 is 0, right guys? That's why this whole term become 0 if salt is equal to acid. Makes sense? Any confusion here? Right? Log of 1 is 0. Okay, that's why if salt is equals to acid concentration, then pH is equals to pKa. What does it mean? What does it mean? It means that point means beaker, right? pH of a whole your titrant, right? Means a whole mixture, whole beaker, is the pKa of that acid if salt and acid are equal. Salt and acid are equal. Okay, that's why let us search what is the point at which salt and acid are equal. What is the point? Okay, so that's easy. So I would say that the point the point the salt and acid are the half of the equivalence point. Okay, at um, at at equivalence point half of the equivalence point, your salt concentration is equals to your acid concentration. Okay, let's realize that how that happened. Okay, suppose that you have 6 mole of acid, and now let's see that what happens at the equivalence point and half of the equivalence point. Now let me make a chart here. Okay, let me make chart. Okay, sorry. Okay guys, now let me make a little bit better. Okay, you don't like, good. Okay, so now let's see that. Okay, so you have acid which is 6 mole. Okay, but you can divide that acid in 2 column. So used, how much is used and how much is left in beaker, left in flask. Okay, how much left in, that is acid. Now let us see the base. Let us see the base. Okay, let us see the base. This is base. Okay, we will see that here. This is the base and this is the salt. First of all molecules are there, all 6 mole are there. You use the 0 at the beginning, right? You didn't run down your NaOH from the burette. And how much is the base? You didn't run down anything, means it's 0. And how much salt will form? 0 at the beginning, nothing. Okay, now let's go to the equivalence point. Okay, let's go to equivalence point. This is equivalence point. Okay, equivalence point, how much mole will be used? it should be completely neutralized, right? Means all of 6 mole of acid should be neutralized. And what will be left then? 0 will be left, right? And how much base you are adding? Then 6 mole base you are adding. And how much salt will form? All 6 mole salt will also form, because it is the, you know that Ha plus NaOH equals to NaA plus H2O. Everything 1:1 ratio. That's why if 6 mole of acid is used, 6 mole of salt will form. What happens with the 1/4 of equivalence point? What happens with the 1/4 of equivalence point means 1/4 times 6 mole is the equivalence point. That is equals to what? 1.5, right? 1.5 mole will be used. So 1/4 of the equivalence point, let's see that one used is 1.5, left is 4.5, base will be also 1.5, salt will be also 1.5. Done? Okay. Now let's go to the 3/4 of the equivalence point. Let's say 3/4 of the equivalence point. 3/4 of the equivalence point means it is 4.5, right? 4.5 ml. 3/4 of 6 means 4.5. So 3/4 of the equivalence point, you are using 4.5 ml. You are consuming. What will be left? 1.5 will be left. How much base you are adding? 4.5 base are using. And how much salt is there? 4.5 salt is there. So that in the 4/4 is no. Salt is 4.5 in your beaker. Acid is 1.5 in your beaker. Okay, let me take another color so that you can see better. Okay, now in 1/4 of your equivalence point, your salt is 1.5 in the beaker, in your flask, but acid is 4.5. In that portion, that time also not equal. 4/4, 3/4 is also not equal, right? Acid is 1.5 left, but the salt is 4.5. What if at the half equivalence point? I told you at the half equivalence point, right? At the half of the equivalence point, half of 6 is equals to 3, right? It means that if 6 mole is there, then 3 mole will be left in and 3 mole will be used. If 3 mole is used, 3 mole is left. And how much base you will add? 3 mole you will add, because neutralizing 3 mole. And how much salt is formed? 3 mole salt is formed. Okay, now let's see that how much left at the half equivalence point in your beaker. 3 mole is got neutralized, but how much is left behind in your beaker, in your flask? 3 mole of acid is there, is still there at the half of equivalence point. And you have salt is also what? 3 mole. You see that half of the equivalence point, salt is equals to acid. Okay, it means that according to what we learned last time, and half of the pH of solution when solution at half of equivalence point is the pKa, right? So let's go to the graph. Look at that here. This is your equivalence point is 25. This is your half of the equivalence point. At the half of the equivalence point, you have how much is the pH? 4. We are done. We are done, right? Let's see that we find the pKa of this particular unknown. Now let me write what is the pKa of that. So the pKa we see it from the graph. Okay, we see from our pH titration. pKa of unknown equals to, it's about 4.1. Okay, and molar mass we also find from the previous titration. Molar mass of unknown is equals to, how much was that? 163.8. These two we got. But from the chart, what is from the chart? Molar mass of trichloroacetic acid is 163.5, and a pKa of TCAA is 0.71, and a molar mass of 3-chloroheptanoic acid is equals to molar mass of that is equals to 1.64.1, and the pKa of that was 4.1, which is correct. Look at that, 4.08. Okay, actually 4.08. Look at that, these two matches these two, right? So that's why, what is your unknown in your box, in your buckets, these blue buckets? 3 chloroheptanoic acid. That's it for today. Okay, we will we will continue this titration next day, because we have to learn for monoprotic acid, diprotic acid. We have to learn this pH titration for diprotic acid or polyprotic acid, etc. Okay, guys, and we will do many of the calculation. Please bring the calculator next day. We are doing lots of calculation, pH calculation, or these titration calculation at the class. Okay, bring the calculator. You need the calculator. I will ask you, heat all the number on your calculator. We are calculating together. Okay, I will also calculate, you will also calculate. 2 or 3 problems we will solve in the class, and that will be very interesting class next day. Okay, thank you so much for today. Any question? That's good. Fine.